Okay, in this video we're going to look at some line segments and circle geometry, and we're going to focus on tangents and chords. And to start with, a tangent line is a line that touches the edge of the circle that is perpendicular with the radius line. And so what we can do is, if we have a length of a tangent line and know what the length of a radius is, we can perform a test to see if a line is tangent to a circle or not by using Pythagorean's theorem. So what I have right here on this left-hand side is I have a line L, which I'm telling you is tangent and is forming this 90-degree angle with the radius. But if this was a problem and I wanted to test to see if this line was in fact tangent, I would do Pythagorean's theorem, where I would do a squared, so leg squared plus leg squared equals hypotenuse squared. And the hypotenuse in this triangle is going to be the sum of a radius plus the distance from the edge of the circle to the end of this line as tangent. And if I set up Pythagorean's theorem and I end up with a true statement, then it's going to be a tangent line. If I end up with a false statement, then it will not be a tangent line. And the next kind of problems we're going to do are going to be looking at chords and tangents. And the three most common ones that you deal with are when you have secant-secant lines with a vertex that lies outside the circle. And the relationship of the line segments are as follows. The distance, in this case I have it color-coded and labeled A, B, C, D, but the distance of the line segment A multiplied to the overall length of the chord, which is A plus B. That product is going to be equal to the length of the segment C times the overall length of that chord, or secant line, that goes from, that's C and D. If I have two secant lines that intersect and have a vertex that lies inside of the circle, the relationship that exists between the line segments is the product between A and B is going to equal to the product of C and D. And lastly, if I have a secant and a tangent line, so I have a tangent line of A and a secant line of BC, the relationship that exists is A squared is going to equal B times B plus C. All right, so here in these first two problems, we want to determine the length of x, whatever x is in this. Let me change colors here. And so I'm looking at what I have here, and they already indicate that I have a 90-degree angle here. And so what we have is we have a right triangle. And so I would just do Pythagorean's theorem. So leg squared plus leg squared is equal to hypotenuse squared. And then I would work to solve from there. So basically I would subtract 7 squared to the other side. And that's going to give me x squared is equal to 35.64. And then from there, I would take the square root of both sides. So the square root of both sides here. And that's going to give me, x is going to be 5.97. Now, the next set here, we want to determine if the line segment AB is in fact tangent to the circle. So we're going to do both of these, number 3 and 4. So line AB, I want to know, is that tangent to the edge of the circle? Well, what we need to know is, does that form a 90-degree angle with a radius line? And so I have my radius line right here in red. And the radius is 13 because the distance from the center to the edge of the circle right here is 13. So that means this is 13. And so if it's tangent, this is going to be a 90-degree angle, meaning Pythagorean's theorem would hold true. And so what we're going to do is we're going to go 13 squared, so leg squared plus leg squared, so plus 16 squared. And see, does that equal the overall length of this hypotenuse here, which is 20. So 20 squared. And I want to know, is that in fact true or not? Well, 20 squared is 400. And 13 squared plus 16 squared makes 425, and so they're not equal. So what that means is AB is not tangent. All right, let's look here at number 4. And so we want to know, same thing, is AB tangent to the circle? And so we're going to wind up doing the Pythagorean theorem test again. And so what would have to happen is this would have to form a 90-degree angle. And so I start setting up Pythagorean's theorem and say, all right, well, leg squared, so 10.5 squared, plus 14 squared. Does that equal this third side here? Well, the length of that third side, we have another, we have our radius at 10.5. So it'd be 10.5 plus 7, so 17.5 squared here. And then I would evaluate that on my calculator. And so 17.5 squared makes 306.25. And the left-hand side, if I evaluate that, that's going to give me 306.25. So they equal each other this time. So since it produced a true statement, that means line segment AB is tangent to the circle. Okay, so let's look at this next one. We have two secant lines and the vertex lies on the outside of the circle. Now, our relationship between the line segments right here is I copied this from the very beginning of the video to be right here beside it. And so I'm going to set up my formula here so that way I can work to solve. And so the way this works is I look and say, all right, well, the distance for x, which goes from the intersection of the two secant lines to the edge of the circle. So I'm going to let that be the A part. So it'd be x times, and then x plus what's left here. So x plus 4. And that's going to equal this, and I do the same thing for the other segment. So 5, which is going to be representing C. So 5 times 5 plus the remainder of that segment there, which is 7. And then I would evaluate that from there. And so working our way to evaluate from here, let's go black. X squared plus 4x is going to equal 60. And so I'd have to get everything on the same side. And so we have x squared plus 4x minus 60 is equal to 0. And we have to factor this. And it's going to factor to x plus 10 and x minus 6. Now I'm working my way to solve here. I get x is equal to negative 10, and I get x is equal to 6. Well, we're talking about lengths of line segments here, so the only one that makes sense for a length of a line segment is if x was positive 6. Okay, now let's look at two secant lines and the intersection lies inside of the circle. And so according to our formulas here, what we would do is we would take the product of the individual segments of the overall line segment and set them equal. So for instance, I have, it'd be x times 15. All right, so I try to color code to match the formula. So it'd be x times 15. It's going to equal, and then the product of the individual segments of the other secant line, so 12 times 10. And then I would work to solve from there. So let me clean that up a little bit. That'd be 15x is equal to 120. And then we would divide by 15. And so 120 divided by 15 is going to give me 8. All right, now let's look at when we have a secant line and a tangent line and relating their line segments together. And the vertex is outside of the circle. So my tangent line here is 12. And so the way this works according to our formula is we take the length of the tangent line and square it. So it'd be 12 squared equals. And then I would take the secant line, the segment that's on the outside, which is x, so x times, and then multiply that to the overall length of the segment, which for this would be x plus 10. And then I would work to solve from there. So let me change back. So we'd have 144 is equal to x squared plus 10x. And I'd have to set it equal to 0 and factor. All right, so that would make 18 and negative 8, which gives me x could be equal to negative 18, or x could equal positive 8, or positive 8. And the only one that makes sense for the length of the line segment is for x to be positive 8.